All right, in this video, we're going to start chapter 14 and talk about antiderivatives, which is the backwards process of getting derivatives. And then over the course of the lessons, we'll talk about what they are for. But let's start with the definition. So antidifferentiation is the opposite process of differentiation. The idea is to find a function, which we'll call here capital F of x, whose derivative is f of x, which is the one that's given. So it's like you want to undo the derivative. So here, in example 1, we have the function lowercase f of x equals 3x squared. And we are asked to come up with an antiderivative for that. We can call it capital F of x just to show that it's not the same as the original function here. And you want to figure out what function was it before the derivative was taken. So you want to undo the derivative to it. So hopefully you remember about derivatives, the power rule, which is that whatever your function was, the power came down and it was reduced by 1. So for example, if your original function was x to the 5th, the derivative would be 5x to the 4th. The idea is that we're looking at this and we're trying to figure out this. So we're trying to figure out what was the original function that produced 3x squared as the derivative. So hopefully you used that little example to figure out that, oh, this must have been x to the 3rd power, because when you do the derivative of that, the 3 comes down, the 3 reduces to a 2, and you get 3x squared. And of course, there could have been a plus 10 or plus 7 or some constant here at the end of the original function, which is why it says to find an antiderivative. There would be an infinite number of these because we don't know if there was a constant at the end. When you do the derivative of a constant, it's just 0 and goes away. So there could have been a constant at the end. So often in this chapter, we'll be sticking a plus c at the end of our antiderivatives to show there could be any constant there at the end. So plus c is the common notation. Next slide is all about notation. And the idea of that plus c. So any single function has many antiderivatives because there could be any constant at the end. And the notation for antiderivatives, or taking an antiderivative, is this symbol. It's this tall, skinny s. F of x, lowercase f of x, this is the function that you're trying to find the antiderivative of. This dx we put here as like a period at the end of our sentence. Like we have to put that at the end of an integration symbol for now. You can think about it as like a closed parentheses. We'll unpack what it means when we start learning about what integration is actually used for. But for now, just know you have to show it there at the end of your integration symbol. And it equals whatever your antiderivative is plus some constant. So basically, in this red box, this is what you're going to be given. And this over here is what you have to find. So you'll be given an f of x, and you're going to have to find the antiderivative, right? So given this function, you will have to find this antiderivative. And I want you to use this notation and all these symbols so that you're practicing writing that tall, skinny s and putting a dx in there. So for example, if I say find each antiderivative, okay, so find the antiderivative. And really, I should say find an antiderivative. And then question 1 is for f of x equals cosine x. I want you to go along and write the antiderivative, also known as the integral. So you'll hear me say the word integral a lot. The integral of cosine x dx. So in place of f of x in the formula, I want you to actually fill in the function that's given. Put a dx there at the end to indicate that's the end of your integral. And then I want you to, on the other side of the equal sign, come up with the antiderivative. What was the function that, when the derivative of it was taken, it spits out a cosine? So we have to remember back from our chapter 11 and 13 days that the derivative of sine is cosine. Therefore, if we are trying to do the antiderivative of cosine, it must have been a sine. And then, of course, we're going to stick that plus c at the end. And that's our answer. But I do want you to be using this notation. Just extend the page here. Let's come up with another example. Might make it a little bit trickier. So what if the function is, actually let's make it a little bit easy and then we'll make it a little bit trickier. So if the function that is given is 4x to the 3rd power, I want to set up this integration symbol, 4x cubed, stick a dx there, and then think what was the function that when its derivative was taken, it spits out 4x to the 3rd. Must have been an x to the 4th power, because now it's an x to the 3rd power. and then the coefficient must have just been a 1, so that when the 4 came down, we got times by a 1 and resulted in the 4 that we see there in the function. And then, of course, we're going to put a plus c. It's a good idea to always just check that you have it right before you put a box around it by quickly doing the derivative of your answer. If you do the derivative of your answer, you should get the function f of x that was given in the question. So indeed, the derivative of sine x plus c would be cosine x. The plus c derivative would drop out, so that's correct. The derivative of x to the 4th is 4x cubed. The derivative of c is 0, drops out, so that is correct. Good idea to check, which is what I'm doing in red. In case you haven't guessed, what's going to make it a little trickier, is changing that coefficient. So what if it hadn't just been that nice 4? So let's say the function given is 2x to the 5th. Okay, so this is going to make it a little more interesting. In order to do the antiderivative, I would recommend you think about the power first, right? If it's x to the 5th in our f of x, then in our capital F of x, or antiderivative, it must have been x to the 6th. But what coefficient would have had to be there so that when you take the 6 down and multiply it by something right there, it somehow is going to spit out this 2. So you have to think about what number must be there at the question mark so that when I bring a 6 down and multiply by, I'm going to get a 2 in front. So 6 times what number gives us 2? You might be sitting there thinking, oh, surely it's 1/3. Indeed it is. And then we put a plus c at the end. Good idea to check our answer before we put a box around that. So if I did the derivative of this, right, I'd bring the 6 down, I'd multiply it by 1/3, 6 times 1/3, and then decrease the power by 1. It would be x to the 5th. So 6 times 1/3 is indeed 2. 2x to the 5th is the question that was given. Therefore, it's correct. And I can put a box around this antiderivative that I have as the answer. Now, I don't want to do this whole process of guess and check every time I need to come up with that 1/3. I don't want to try to mental math my way through it. So we can write down some helpful sort of a formula that'll help us do this power rule in reverse every time. And it turns out that the way to get this antiderivative without just guess and check, okay, is to, and I'll write it over here again, the antiderivative of 2x to the 5th dx, it's just to keep the 2, so the coefficient that was there, keep that 2, multiply it by, keep the 2, decrease the power by 1, increase the power by 1, trying to figure out a formula here, and divide by the new power. That will do the trick. Okay, so we want to keep the 2, so keep whatever coefficient was there, then increase your power by 1 because you know you're going to need to increase that power, and then divide the entire expression by the new power. Of course, stick a plus c at the end, and then reduce that fraction. So if we have this 2/6, it'll be that 1/3. And that's what we get 1/3 x to the 6th plus c. So that we don't have to mental math it every time. Keep the coefficient, increase the power by 1, and put it over the new power. To keep going with these notes, so it's the basic integration formula that we're going to want to know. It's basically the backwards version of all of the derivative formulas that we had to know. So for example, the antiderivative of cosine is sine, and that's because the derivative of sine is cos. The antiderivative of sine x is going to be negative cosine x. And these are also in your formula booklet, and you could probably just figure them out based on what you know about derivatives, but still useful to have a little cheat sheet. The antiderivative of e to the x, you might have predicted, is e to the x, and that's because that works both ways. Derivative of e to the x is still e to the x. The antiderivative of 1 over x is ln x. This was a function we had to know back in our derivative days, that the derivative of ln x was 1 over x. This one's an interesting one because you can't go backwards with it. So, and I'm putting this in red on purpose. The antiderivative of ln x, we don't need to worry about. We don't have any rules that we ever had to learn where the derivative answer was ln x. We only ever had to get the derivative of an ln function. So we never had ln as the output. Therefore, we're not going to be going backwards with it. So we're not going to have to worry about that one. What are some of the other ones we did? Tangent, if you need it, is going to be in the formula booklet. It's very rare that it comes up, but it's there if you do need it. And then I think there's just the power rule, which I am opening the formula booklet to try to show you exactly how the formula booklet indicates that. Yes, there's just the one more. All right, and this is the power rule that we sort of just went over. But the way that the formula booklet shows it, it's actually the most complicated looking one. That's why I saved it for the bottom. Would be if you're trying to do the antiderivative of some power, as we just talked about, you're going to want to keep whatever coefficient is there. So let's say there's an a. I'm adding that a. It's not actually in the formula booklet, but I think it's important. Keep the a, increase the power by 1, and put the entire fraction over the new power. And then don't forget the plus c. Now that one looks more confusing written out formulaically like that than it actually is in practice, and that's the one that we're going to end up using the most. None of these rules account for things like chain rule and product rule, which of course we will be going through over the course of the chapter, but we got to start with the basics and get us freshened up again about our derivative rules. So let's just practice a few. We can skip that slide. So let's just practice a few. Here we have evaluate these basic integrals or antiderivatives. In this first example, we haven't done one like this where there is a 3, like a coefficient, in front of a cosine function. We did one where there was a 3 or I think it was a 2 in front of x to the 5th, and I showed you just keep the 2. So any coefficient that's in your function should still be there in your antiderivative. So when I'm trying to evaluate this antiderivative, I'm going to keep that 3. I'm going to do the antiderivative of cosine x, which I know is sine x, and then I will put a plus c at the end. Right? So keep any coefficients that are there, do the antiderivative of any term, and then don't forget a plus c at the end. And then for part B, let's see if I can just drag this out of the way. For part B, slightly interesting because it goes term by term. Conveniently, we are able to do the integral or the antiderivative one term at a time. Just like when we do the derivatives, we can go one term at a time. So you can imagine that we are doing the antiderivative of x to the 3rd dx plus the antiderivative of x squared dx, though you don't ever need to write this entire step. I just wanted to show you that that's what we are doing. In each of these cases, it's a power rule that we need to follow. So the power rule says keep the coefficient, which here is just a 1, increase the power by 1 and put it over the new power. This would have a plus c. Over here, we're going to do the same. We're going to increase the power by 1 and put it over the new power. And over here would have a plus c. There's a plus in between them. I do not need to put a separate plus c for each of these because whatever random constant 1 plus random constant 2 is just another random constant. So I can just go term by term. X to the 4th over 4 plus x to the 3rd over 3 plus a single constant c that might be there. And then for the sake of more practice, in each of these, it looks like it's about to get so much harder, like a quotient rule is involved or something. But I intentionally put these here to show if you're just dividing by a single quantity, or indeed multiplying, you could just distribute it first and then go about using your regular integration rules or antiderivative rules. In this case, we want to just simplify first. So I'm going to keep writing this integration symbol as I simplify because I haven't actually integrated anything. All I'm talking about doing is taking this t to the 5th and actually dividing it into each term. Notice they changed t, so the end of my integration is a dt instead of dx. Still haven't simplified, I still haven't done the antiderivative, so I'm keeping this s symbol here. I'm still just simplifying. So hopefully you can see how t to the 3rd over t to the 5th just became t to the negative 2. These t to the 5ths cancel out and leave us with just a minus 3. And so now I'm ready to get the actual antiderivative. I simplified the original question to what's here in this bubble, and now I'm actually ready to do the antiderivative. So antiderivative of t to the negative 2nd power, it is a power rule. I'm going to now put an equal sign, drop the s symbol because I'm doing the antiderivative, increase the power by 1. Whoa, just said I was going to drop that symbol, and I wrote it by accident. I'm going to keep t, increase the power by 1, put it over the new power. A minus 3 is interesting because I do want to increase the power by 1. When you're doing an antiderivative, the constants don't drop out. Indeed, there is a t attached to that 3. Just right now it's invisible because it's to the 0th power. But if I increase that by 1, it's actually going to become minus 3t to the 1st power over 1. Of course, I will not be showing that 1st power or that over 1. Once I clean this up a little bit, you'll see this whole thing, it's just a negative 1 over t, because I don't like t to the negative 1 being in my final answer. Got to drop that to the bottom. And then this, of course, is just minus 3t. Got to put a plus c at the end, which I failed to do before that step. And that's the antiderivative there. Similarly, in this problem, we want to simplify first. So it's going to be keep the s, or the antiderivative symbol, as you simplify each term. Because you haven't actually taken the antiderivative yet, you could tell that's going to become a thing with me. I really want you keeping that s symbol, that antiderivative symbol, until you've actually done the antiderivative. But still I'm simplifying, still I'm simplifying. Finally, I'm ready to do the antiderivative, so I can drop the s. When I have x to the negative 1 power, if I try to increase that by 1, I'm going to end up with x to the 0th. That should be a little red flag for you. That x to the negative 1 is special. It's actually 1 over x. And if I arrow back to one of our formulas, perhaps you'll remember where we have seen a 1 over x before. Indeed, if I'm doing the antiderivative of 1 over x, I have to remember that's the special one. I do not want to have x to the 0th in my answer. Indeed, the antiderivative of 1 over x is ln x. The antiderivative of 5x squared. Keep the 5, increase the power by 1, put it over the new power. I don't need the dx anymore, but I do need to stick a plus c at the end. And this is as simplified as that's going to get. So you can put a box around that and call it a day. All right, that's our first crack at antiderivatives.